So imagine, just for a second, the stress of trying to parallel park your car on a really busy, like incredibly narrow city street.
Oh yeah, the absolute worst.
Right. You've got cars honking behind you, maybe a cyclist squeezing past your side mirror, and you are just praying you don't scrape the bumper of the car behind you.
Your heart rate is up, your palms are totally sweating on the steering wheel.
Exactly. Now, I want you to take that exact feeling of anxiety and, multiply it by about 1,000.
Which is, frankly, entirely justified. Because in this scenario, your car is over 70 feet long,
Yeah.
and the bumper you might scrape is worth more than most people's houses. Plus, the narrow street you're navigating is actually a highly congested indoor industrial space that is just packed with explosive jet fuel.
Welcome to the deep dive. Today, we're putting you right in the middle of ground handling for multi-million-dollar aircraft.
It's a massive, shockingly expensive problem that the aviation industry deals with every single day.
And to understand how they are trying to fix it, we are exploring a really fascinating stack of sources you sent over. We've got blueprints, technical specifications, and system overviews from a company called Safe Room Designs.
Right, specifically looking at their GBS G5 Hangar series.
Yeah, and a software integration they call Hangar AI.
Our mission today is to really unpack how the industry is solving this whole problem by combining cutting-edge predictive software with precision-engineered physical architecture.
It's essentially a masterclass in how you engineer human error completely out of an environment where the margin for error is, well, basically zero.
Exactly.
Okay, let's unpack this. Before we get into the futuristic tech and these massive architectural blueprints, we really have to establish why any of this is actually necessary.
Right, the baseline problem.
Yeah, because looking at the stack of sources, the baseline reality is pretty jarring. The hangar floor is a surprisingly dangerous place to be in an airplane.
It's counterintuitive, right? Most people assume the danger in aviation is up at 30,000 feet.
Dealing with turbulence or, engine issues.
Exactly. But the ground operations, specifically the act of moving an aircraft into and out of a tightly packed hangar,
Yeah.
that is consistently one of the highest risk operations in the entire industry.
There is a photograph in our source stack that really drives this home, and I want to describe it for you.
Oh, the tail section picture.
Yeah, it's this stark daytime shot of an aircraft's tail.
Yeah.
The paint job is pristine white with this sharp red and black stripe pattern.
But you almost don't even notice the paint.
Not at all, because the entire back edge of the tail is just violently crumpled.
Yeah.
I mean, it is dented inward, the metal is completely buckled, the structural rivets look like they've literally popped out.
It's brutal.
Honestly, it looks like a giant took a hammer to it, or like it was backed at high speed into a solid brick wall.
And in the aviation industry, they have this surprisingly casual, almost dismissive term for this kind of catastrophic damage.
Right.
They just call it hangar rash.
Hangar rash. I mean, it sounds like a mild skin irritation you get from wearing a cheap sweater, not a multi-$100,000 structural failure.
Yeah, the term definitely downplays it.
So how does this even happen? I mean, these are highly trained professionals moving these planes. Why are they bumping into walls?
Well, it really comes down to the severe physical constraints detailed in the documentation. Just think about the geometry of the situation.
Okay.
You are dealing with incredibly tight clearances. Hangars are astronomically expensive real estate.
So they want to cram as much in there as possible.
Exactly. Operators are financially incentivized to pack as many aircraft into them as physically possible. It's basically a giant jigsaw puzzle.
Right.
Then you have the issue of limited visibility. You're moving wingspans that stretch for dozens of feet.
And the guy driving, right?
Yeah, the person actually driving the tug, which is that little low-profile vehicle, pulling the nose gear of the plane, they're sitting incredibly low to the ground.
Oh, wow.
They often literally cannot see the extremities of the aircraft they are towing.
So they can't rely on their own mirrors. The sources say they are relying almost entirely on manual coordination.
Yep, the old-fashioned way.
That means guys on the ground in high-vis vests with those glowing wands walking alongside the wings, trying to yell or signal over the roar of an active flight line to the tug driver.
It's a logistical nightmare.
It's like trying to navigate a grand piano through a crowded studio apartment. But in this case, even a tiny scrape on the doorway costs hundreds of thousands of dollars and grounds a scheduled flight.
If we connect this to the bigger picture, it highlights a massive paradox in modern aviation.
What do you mean?
Well, the industry spends billions of dollars and countless engineering hours making planes incredibly safe in the air. You have triple redundant flight systems, advanced weather radar, automated collision avoidance software in the sky.
All the bells and whistles.
Right. But the second that plane lands and needs to be parked inside a building, we suddenly revert to a guy blowing a whistle and waving his arms. The vulnerability isn't the flying, it's the parking.
And the cascading consequences of that vulnerability are severe. The documents point out that accidental collisions, whether it's an aircraft hitting the structural steel of the hangar, hitting a stray piece of ground equipment, or the ultimate nightmare, hitting another parked aircraft. It all leads to damaged wings, crumpled tails, and compromised fuselages.
Which triggers an absolute financial avalanche.
Oh, I bet.
The aircraft is immediately grounded. That means if a commercial jet gets hangar rash, multiple flights are canceled, and hundreds of passengers are stranded.
And for private jets.
If a private charter gets hit, executive schedules are completely ruined.
Wow.
And beyond the operational delays, you have rising insurance premiums across the entire fleet and incredibly expensive repair bills. You can't just slap some Bondo on an airplane wing and paint over it.
Right. The structural integrity has to be fully recertified.
Exactly. The financial bleed is continuous.
So if manual coordination and human reaction times are the root causes of these insanely expensive ground collisions, it creates a very clear problem-solving logic.
You have to find a way to remove the human reaction gap entirely.
Yes. And that naturally brings us to the software solution outlined in our sources, Hangar AI.
This is essentially the digital guardian designed to completely oversee the physical space.
The documentation outlines a specific 5-step process for how this system operates, systematically eliminating the reliance on a human spotter, noticing a hazard at the last possible second.
Right, so let's walk through those.
Let's slow down and really break down those 5 steps because I want you to understand exactly how this works. Step 1 is detect.
Detect, yes.
The sources say they use cameras and sensors to capture real-time aircraft positioning. But hold on, an airplane has a very bizarre geometry.
It really does.
It's not a neat little rectangular box like a car. You've got swept wings, tail fins, engine cowlings. How is a camera reliably detecting all of that in a crowded space?
Well, it's not just a standard optical camera taking a flat video. They are using advanced spatial sensors that map the three-dimensional volume of the space.
Oh, interesting.
It captures the exact geometry of the aircraft, the sweep of the wing, the height of the tail, and tracks its precise positioning across the entire hangar floor.
Okay, so it sees the shape, not just a picture.
Exactly. And it's not just tracking the plane being moved, it's simultaneously tracking every other aircraft and piece of equipment in the building.
Which feeds directly into step 2, which is analyze.
Right.
This isn't just a video feed streaming to a bored security guard looking at a monitor. The AI brain is taking all that 3D spatial data and processing movement speed, trajectory, and proximity in milliseconds.
It's essentially holding a constantly updating geometric model of the hangar in its head.
It is constantly doing the calculus of every moving object in that space.
Which is what enables step 3, predict. And this is really the absolute core of the system.
The software forecasts potential risks or collision paths well before they become critical.
Precisely.
Okay, wait, I have to play the skeptic for a second here.
Go for it.
Isn't this basically just a, highly expensive, scaled-up backup camera for an airplane?
People ask that a lot.
Because when I'm parallel parking, my car beeps if I get too close to the car behind me. Is this really any different from a glorified parking sensor?
It's a really important distinction, actually, and it comes down to the difference between reactive technology and predictive technology.
Okay, reactive versus predictive.
Think about your car's backup camera. It is entirely reactive. It beeps when you are actively about to hit a bumper or when you are already dangerously close.
Right, it goes beep, 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 crash.
Yay.
It's just telling you that you are currently messing up.
Exactly. The warning happens in the present moment of danger. But Hangar AI operates in the future.
In the future.
Because of that predict step, the AI anticipates the collision path based on the specific speed of the tug, the known turning radius of that exact model of aircraft, and its current trajectory.
So, to put you in the hangar for a second, imagine a tug is pulling a massive Gulfstream jet around a tight corner.
Okay.
The wing is sweeping in a huge arc. The AI isn't waiting to see if the wing gets close to a maintenance cart.
No, not at all.
It's looking at the math and saying, if this tug continues at 2 miles per hour at a 15-degree turning angle, that wingtip will occupy the exact same physical space as that maintenance cart in exactly 4.2 seconds.
Precisely. It stops the sequence before the emergency even develops.
That's
It
incredible.
transforms the safety protocol from reactive damage control to proactive prevention.
And then you have step 4, which is alert.
Right, once it predicts that future collision, it sends immediate warnings to the ground crews.
The documentation notes these are instant visual and audio cues. Operators can even set up customizable safety zones based on the specific layout of their facility.
Which is super helpful for weirdly shaped buildings.
Yeah. And finally, step 5 is record. Every millimeter of movement is logged.
Which is huge.
If an incident or even a near miss occurs, you have an automated objective log of exactly what happened. I imagine that's huge for regulatory compliance and insurance audits.
Oh, absolutely. No more pointing fingers between the tug driver and the wing walker.
It's all on the digital record.
Plus, it also feeds back into the system's own intelligence.
Oh, right, the machine learning aspect.
Yeah, Hangar AI actually learns from historical movement patterns within that specific hangar to improve its routing and hazard predictions over time.
So it gets smarter.
Exactly. Your car's backup camera doesn't get smarter the more you park, but Hangar AI does.
To really visualize how all-encompassing this is, there's a highly detailed patented image in the files.
I love this image.
It's so cool. It shows a sleek private jet parked inside a hangar, and emitting from the tail section of the aircraft are these bright, red, concentric, radar-like rings.
Yeah, it visually illustrates that the system provides 360-degree awareness.
It completely eradicates the concept of a blind spot.
But here is the critical pivot in our sources.
Okay.
If AI is this incredibly precise, sensitive brain capable of millimeter-level predictions, it creates a brand new problem.
Which is?
A brain that precise needs a perfectly controlled environment.
Right. You can't just mount a 22nd century AI brain inside a drafty 19th century barn. If you have severe temperature swings, sudden drafts, or water intrusion, it could mess with the spatial sensors.
Not to mention the delicate avionics of the aircraft themselves.
Which means safe room designs had to literally reinvent the hangar from the ground up to protect the system.
Software is totally useless without the right hardware.
And that brings us to the structural blueprints in our stack. The physical fortress itself, the GBS G5 hangar.
This thing is a beast.
I am not an architect, but I spent hours geeking out over the sheer scale and engineering precision in these specifications.
It's impressive.
Let's pull you out of the software for a minute and put you in front of this building. To give you a sense of the sheer scale we are talking about, according to the exterior wall schedules, the GBS G5 is 116 feet long, 112 feet wide, and the ceiling height is a towering 36 feet.
You are looking at over 16,400 square feet of exterior wall space alone.
And the door.
Oh, the door is massive.
Imagine standing in front of this building. The rough opening schedule details something called the NR Arco hangar door.
Yeah.
The dimensions are listed as 1,296 inches wide by 360 inches tall.
Which is wild.
To save you the math, that is a single door opening that is 108 feet wide and 30 feet high.
You could comfortably drive a 3-story apartment building right through that opening.
Right.
But you need an opening that massive to accommodate the wingspans, obviously. But the engineering challenge is staggering.
How so?
Think about the structural integrity required to hold up a massive roof when an entire 108-foot side of your building is essentially missing to let the planes in.
Right, there's no wall there holding the roof up.
Exactly. That's why the materials and the assembly methods they're using for the building envelope are so critical.
Here's where it gets really interesting. I want to look at the main wall assembly, which the blueprints call the F-160 tilt-T wall assembly.
Tilt wall, yeah.
First off, tilt wall means they cast or assemble these massive panels flat on the ground and then literally tilt them up into place with cranes.
It's a really efficient way to build.
The blueprints show they use exactly 116 of these standard panels for the exterior. But it's the makeup of these panels that is just wild.
Yeah, let's break down the layers of that F-160 assembly because it's brilliant.
What exactly are we looking at here?
Well, the core skeleton uses single 8-inch by 14-gauge steel studs. Very strong, very standard.
Okay.
But both the interior and the exterior faces of that skeleton are clad in 12-millimeter Megcrete sheathing.
Megcrete. That sounds incredibly heavy-duty. What actually is that?
It's a specialized magnesium oxide board.
Okay.
Think of it as a super material that replaces traditional drywall or plywood. It's incredibly durable, moisture resistant, and most importantly, it is highly fire resistant.
Which makes perfect sense when you consider you are parking tens of millions of dollars of machinery that is quite literally filled to the brim with highly flammable jet fuel. The blueprints explicitly note that this wall assembly provides a 1-hour fire-rated construction.
Which gives you crucial time in an emergency.
Right. But what about the temperature control?
Yep.
Because sandwiched between those layers of Makecrete, the specsless EPS insulation with the thermal break, achieving an R49 insulation value. Walk me through that.
Sure. So EPS stands for expanded polystyrene. It's a highly dense, rigid foam insulation.
Okay.
But the real magic phrase there is thermal break.
Thermal break.
Yeah. Here is why that matters. Steel studs are highly conductive.
They transfer heat.
Exactly. If it's freezing outside, the steel will literally suck the heat right out of the building's interior, acting like a bridge for the cold.
It's like if you leave a metal spoon sitting in a pot of boiling water.
Mhm.
The handle gets burning hot because the metal conducts the heat all the way up.
Exactly. A thermal break is literally inserting a non-conductive material into that assembly to break the bridge. It stops the temperature transfer dead in its tracks.
Oh, wow.
By breaking that thermal bridge and using dense EPS, they achieve an R49 insulation value. To put that in perspective, an R49 value essentially means this hangar is insulated like a giant industrial deep freezer.
So imagine you're standing inside this space. It might be a total blizzard outside. But because of this thermal break system, the interior climate doesn't shift a single degree.
Not at all.
The heating and cooling costs aren't bankrupting the operator, and those sensitive AI sensors aren't dealing with fluctuating environmental variables.
Right, and they apply that exact same extreme isolation to the roof.
Okay, let's look at the roof.
The roof panel schedule lists 405 custom panels. They utilize 10 inches of GPS foam, which is graphite polystyrene, meaning it actually reflects radiant heat.
10 inches of foam.
Yeah, and all of that sits on top of an open web steel joist system and structural Q-deck decking.
Let's translate that for a second. An open web steel joist looks a bit like a metal spider web.
Right.
It's a zigzagging steel truss that is incredibly strong but lightweight, and it leaves empty space for running cables and HVAC ducts.
Super practical.
And the Q-deck is that heavy, corrugated steel decking that forms the solid base of the roof. It is basically an impenetrable thermos from the top down.
And they didn't forget the ground either. To anchor it all, the construction details show this massive structure sits on a concrete strip footing foundation.
Okay.
But they wrap that foundation in a blueskin waterproofing system, which is a self-sealing, rubberized asphalt membrane.
Wow.
Yeah, and then they lay down a 10 mil polyvapor barrier over compacted gravel before they even pour the concrete floor.
A vapor barrier is essentially a thick sheet of industrial plastic that stops any ground moisture from wicking up through the porous concrete.
Because moisture is the absolute enemy of aircraft maintenance.
Oh, for sure. It causes corrosion, it ruins avionics. They have literally sealed this building off from the earth itself.
What's fascinating here is the absolute synergy of the system.
How do you mean?
Well, this isn't just a building that happens to have some smart cameras inside it. The structural engineering is fundamentally enabling the software to work.
It's like building a high-end gaming PC.
Yeah, good analogy.
You don't take a multi-thousand-dollar top-tier graphics card and just drop it into a flimsy cardboard box.
No, you'd ruin it.
You buy a specialized chassis with optimized airflow, dust filtration, and rigid structural integrity to protect the components. That is exactly what the GBS G5 hangar is doing.
It's a custom-built, climate-controlled, fireproof chassis.
Designed specifically to house the Hangar AI motherboard and the multi-million-dollar components, the airplanes that go inside it. The building and the software are essentially one unified machine.
And it is a highly scalable platform, too.
Yeah.
One of the floor plan views in our stack, Z100, shows the hangar comfortably housing a large private jet alongside an enclosed office area and a parked car.
Right.
But the documentation for Hangar AI explicitly states that this technology is designed to scale way beyond a single private jet.
Right. They list commercial airline hangars, military aviation facilities, aircraft manufacturing plants, and large MROs.
Which are aircraft maintenance, repair, and overhaul facilities.
You can take this precise hardware-software integration and scale it up to manage the intricate ballet of an entire commercial fleet.
Exactly.
So what does this all mean for you? Even if you don't own a private jet and, you're never going to manage an airline maintenance facility, there is a fundamental lesson here about the evolution of workspaces.
There really is.
For decades, we just accepted that large-scale physical movement in industrial spaces meant accepting a certain degree of friction.
Human error, blind spots, costly accidents.
Exactly. We just wrote it off as the cost of doing business.
But this stack of blueprints and AI specs proves that friction is no longer mandatory.
Right.
By combining intelligent predictive vision systems with highly insulated, precision-engineered physical infrastructure, you can essentially engineer human error completely out of the equation.
It's about designing an environment that actively protects the assets inside it, rather than just passively housing them.
It completely shifts the paradigm from reacting to accidents after they happen to architecting a space where accidents mathematically cannot occur.
This raises an important question, though, and it's something I want you to think about as we wrap up.
Yeah, let's hear it.
We've seen that AI can now perfectly predict the exact trajectory of multiple moving aircraft in a confined space, mapping it against the precise dimensions of a megastructure like the GBS G5. If the system's brain is this smart and the environment is this controlled, how long until the entire concept of manual coordination is entirely obsolete?
You mean taking the human driver out of the tug completely?
Exactly. Will the hangars of the near future just smoothly, autonomously move the planes themselves?
I mean, imagine these massive facilities shuffling multi-million-dollar jets around like a perfectly choreographed robotic sliding puzzle, while the pilots and the ground crews are at home sleeping.
It's entirely possible. The software and the hardware are already talking to each other perfectly. The next logical step is simply letting the building drive the planes.
That is an incredible, slightly eerie image to leave on. The fully autonomous, robotic mega hangar.
It definitely makes trying to parallel park your car on a busy street seem a whole lot less stressful by comparison.
Just a little bit.
Thank you for joining us on this deep dive. Keep questioning the environments around you, keep looking at the blueprints of the future, and we'll see you next time.